Thank you. I'm glad to be here. Yeah, I'm never going to hear the end of the rake version jokes, am I? All right. Good. We've got screen, we've got slides, my clicker works, and we're going to start off with some fun. Before we get into anything else, I just want to show you a little bit of what we've been playing with back in the office. So let's bring up this. This is a Parrot AR drone. You can see it flying there. That's under the control of one of my coworkers, Karen Meyer. That's her drone. And we have a nice big open atrium area in our office that allows us to fly these things right there in the office. So a lot of lunch times or after work, we'll go out there and we'll fly the drone. There's Karen. Now, what you need to realize is I'm videoing this, and I'm doing it from my drone, which is also flying. That's why the camera is a little bit wobbly. We're trying to fly around the big open area there at the corner. And I'm trying to do the maneuver where I go around and try to keep her in my field of view. There, a little close to the wall there, Karen. Okay, we're good. And we're just having fun playing with these things, just moving them around. I'm not going to make you watch the whole thing here, but let me show you what happens when your drone runs out of battery. I'll skip over here to the end. Okay, I'm watching, and there we go. So, flying drones, awesome fun. I recommend you grab one and have a good time with it. I'm going to move this microphone a little bit more in the middle. So can you still hear me? Are we good? Yeah, all right, good. So, we're going to talk about Ruby, we're going to talk about code, we're going to talk about threads and events, and we're going to talk about flying robots. So, before I get into that, I want to share with you this concept of a narrative chart, because we're going to be telling some stories here, and I think telling stories is a very interesting thing to do. And one thing you can do with movies is to go through and chart them and see how the narrative moves along and how the protagonists in the movie move around throughout the movie. So the first one is 12 Angry Men. Has anyone seen this one? This is a classic. This is awesome. And it's an entire movie where you sit in one room with 12 jurors and they argue for the full length of the movie. But it is fascinating. It's a good psychological drama and very good. So here's the narrative chart for 12 Angry Men. 12 men in a room. They don't move around much. Here's another movie you might be more familiar with. How many have seen this one? If you don't raise your hand, you lose your geek status. I have a friend whose girlfriend has not yet seen this movie. And yeah, that's exactly. What? He's got to correct that very soon. So this is the narrative chart for Star Wars. You can see, so here's Luke all by himself, Obi-Wan, C-3PO, R2-D2, and Leia are together. The droids escape. Over here is the whole rescue, Leia from the Death Star scene. Here's the duel where Obi-Wan dies. Over here is where the Death Star is blown up, and you can see Han and Chewie fly away and then come back in the nick of time. So you kind of see a whole narrative thing go there. And they actually plot this thing out for those three movies, the real movies. So this is from XKCD. So go look this up if you want to see that. They have a bunch of other movies out there, but there's one more I want to share. Okay, so you've seen this one too. I'll ask this, how many people have seen it more than once? Yes, you must see this one more than once. How many people understand what was going on in this movie? Exactly, because this is the narrative chart for that movie. Okay. Excuse me. So how many people here, I want to ask this question. How many people here consider themselves primarily hold your hand up if you're a Ruby programmer, Ruby developer. Okay. Put your hand down if you consider yourself primarily a web developer. And that includes Rails or Sinatra. So leave your hand up if you don't consider yourself primarily. Well, okay, good, a couple people up there. I think I've been using Ruby since before Rails. So to me, Ruby is a general purpose program. I've used it for lots of things. I've used it for scripting my tools. I got so frustrated with the build system at one client I worked at, I wrote an entire build system in Ruby just to make things easier for me. So I'm very much of the mindset that Ruby is not merely the web, but not everybody out there is like that. And I think they see Rails and they kind of forget Ruby's involved and they think the whole thing is tied up and it's only good for web programming. So I want to encourage you to consider using Ruby for non-web projects. And there's lots of things out there that you can do. Build tools, scripting, back-end stuff, and I'm sure you'll hear more about this throughout the weekend here, but I want to talk about a particular project that we did that was refreshingly not web-based. Now, it was tied to a web. It was kind of a back-end for some processing. But in this story, I'm going to tell you the story about this project, kind of in the abstract. I'm not going to get into details about it. It was a non-web project. It will involve lots of code. You will see code examples in this talk. We will talk about threads, and we will talk about events during this time, and we will also talk about flying robots. Unfortunately, the project we work on didn't really use flying robots, but I can't resist tying them in somehow. So hopefully we'll learn a little bit about Ruby through this particular discussion. Now imagine, this is an analog to our real project. When we got there, the client had several hardware managing systems set up. And let's say it was for Roombas and general purpose robots. And they would have a lot of Roombas and a lot of robots out there, and they would communicate with their servers talking to manager programs. There was a program to manage the Roombas, there was a program to manage the general robots, and they asked us to write a drone manager program. I'm very excited about this, because yes, this is a really cool thing to do. And again, the drones will be connecting with TCP/IP, they'll be creating sockets, and they'll be sending information, and we need to have a manager talk to them. Now, the key thing here is that this is not a web program. This is a program talking over sockets to hardware devices out there in the wild. It has to support thousands of connections all at the same time and still pump the data through it. Now you might say, thousands of connections, that seems like a lot, and it does, it is. The original programs were written in Java. But I've written Java before, I'm not scared of writing Java, but coming into this thing, I was thinking, you know, there's no reason we could not do this particular manager in Ruby. It turns out that the Java programs are about 4,000 lines long. That's how big they are. The Ruby program, when we got done with it, was between 300 and 400 lines. So, 10 to 1 difference. Now, I'll let you know up front that the original versions were fairly smart programs. They did a lot of processing on the data passing through. That proved problematic in that these managers you want to have up running all the time. So making changes to them was problematic, because if you change a program, you have to drop the manager, and all the hardware devices have to reconnect, which that caused a problem they referred to as the thundering herd. When everything reconnects all at once, you got to take care of all that data. So we decided to keep the drone manager dumb. He was going to be a data pump only and not do a whole lot of smart processing. So that is one reason for the reduced lines, but maybe that accounts, 2,000 rather than 4,000 lines. So we were still greatly reduced in the number of lines of code to do the Ruby version. This is the whole system here. I'm not going to talk about this part, but I want to let you know it exists. The manager programs talk to some kind of message queue in the background. There was a set of workers that pulled messages off the message queue and updated the database with information from all the different managers. And then there was a Rails web portal front end that pulled data out of the database and displayed them to the users. And the web program and the workers could both send messages back into the queue and to each of the managers, which would further forward those messages out to the hardware devices. So there was complete control from the web all the way out to the hardware devices. That was really, really cool. But we're going to talk about this part right here. And in fact, I want to concentrate just on the drone part and what we did to make that work, how we accomplished the job of talking to thousands of connections really fast in Ruby. So for our talk purposes, we have to establish a protocol between the drones and the manager. They're going to talk over a socket connection. It's going to be a text-based protocol. And we're going to call that protocol the Flying Robot Objects with Navigations protocol, FROWN. FROWN looks like this. It's a very simple protocol. It has 4 commands in it. 2 commands are sent by the drone. There's a position command where the drone reports where he is at that point in time in XY coordinates. And there is a name command where the drone reports its own name. Coming back to the drone, there are 2 commands. One is a name query. And when the drone receives this command, he should respond with the name command going back out. So if the software needs to know a name of a drone, he will ask and the drone will tell him his name. And finally, there's a crash message that informs the drone he is occupying the same physical space as another drone. And therefore, he should crash and he should disconnect from the network. He is down, he is dead. So that's our FROWN protocol. This is an example of that. A drone might send the position 5-6. The monitor gets that. The monitor says, oh, here's a brand new drone. I don't know what he's called. So I'm going to send the name message back to the drone. The drone responds, says, hey, I'm drone A. And then he'll update his position as he moves around, kind of randomly walk. And then when the monitor detects a crash, he'll send a crash message, and then the drone will disconnect at that point, and he'll disappear off the network. Okay, so that's the drone. Here's the monitor. The monitor's job is to display in a high-definition graphics environment the positions of all the drones that it knows about. I particularly like the use of colons to represent the 4 rotors of the quadcopter. The monitor's set of commands will look like this. He's also talking through a TCP/IP network. And the data we're sending him is a little more sophisticated. It will be JSON serialized versions of these data structures. So incoming, he'll get a drone ID. So the drone manager here, every time a drone connects, will create a ID for that drone that is unique. And when he sends messages to the monitor, he will tell you what drone it is. He will get connected and disconnected messages when drones connect and disconnect. And he will also get the data messages. Whenever a drone sends a FROWN message, he will get a data message that looks like this. Going back from the monitor to the manager will be messages that look like this, a message for this particular drone and this particular FROWN message right there. And I think it's particularly cool that we designed this protocol to use arrays in this direction and hashes in that direction. I don't know why. I didn't actually even notice we did that until I was making the slide up and saw both of them on the same page at the same time. We should fix that. So let's look at the code that it takes to do this. Now this is going to be the drone code right here, but this is a very close analog to what we wrote in real life for our client. There's lots of details omitted, error handling, logging details and things like that I'm leaving out so we can concentrate on the code that we need to make this whole thing work together. So first off, this is the manager program. This is the program that sits right in the middle, talks to the drones, and talks to the monitor. So his job is to pass data back and forth between the drones and the monitor, tagging the data from the drones with appropriate ID, and when the data comes back from the monitor, to look up the drone based on the ID and send it to that particular drone. So the main program looks something like this. We're using Event Machine. Event Machine is a Ruby library that allows you to do essentially Node.js stuff. Evented I/O, so that you get callbacks when I/O happens, and you respond to particular events as things happen. The main program is a big event loop set up by the run command on Event Machine, and from here to here, this configures the servers that we say our system needs. We have 2 servers. One is a monitor session here, and he's set up to be on this host monitoring this socket. And the drone session here also set up, and he's on a different port right there. And that sets those things up, and actually I had red highlights here so I could click like this and didn't have to point with my laser pointer. So there you go. So we set up 2 servers. Each server is monitoring a particular port for incoming messages, incoming connections on the TCP/IP. Now the sessions, let's look at the drone session in particular. This is the part of our program that looks for incoming messages from the drone. And the server, or actually the monitor session is very much like this because they're all event machine servers. So when an incoming connection is made, event machine will go and create a new object of type drone session. So that happens when a drone connects up. After we create a drone session, he will get a post init command. So after event machine is done and he's ready to start using the session, he'll send him a post init flag, and then our drone session can do any final setup that he needs to do right before he's ready to start receiving messages. When data comes in, event machine will break it up into line by line input, and each line he will send to us with a receive line message. So receive line gets called on our drone session. Finally, when the connection is closed, the session will receive an unbind command. And then finally, there's also, so these 3 messages here and the create is all handled by event machine. Our software can, if it detects an error, wants to shut down for some reason, he can call the close because and give it a reason, which then in turn calls the close message, which will in turn cause unbind to happen and the whole thing begin to shut down. But this is called by our software, not by event machine. All these other methods here are called by event machine itself. So let's look at a drone session. To create it, we create a module called drone session. This is weird in event machine. There's a number of different ways you can do this, and we decided to go with the module approach. You take a module, you mix in this line text 2 module, and that's what allows us to receive lines of data rather than packets of data. So event machine will break that up into lines for us. The post init, this is what happens after a connection is made and we're ready to start receiving data, but before we get the first message, what we want to do is log the fact that we've got a new connection, kind of log what IP address it's coming from, and then also save this session object in a big hash collection based upon the connection ID. The connection ID is a UUID that we generate that is unique for every session that gets created. So we save that, we save a reference to ourselves in a big hash based upon the connection ID. When we receive a line of data, the first thing we do is enqueue. Enqueue is a private method in the drone session that actually sends the data to the monitor. We'll see that in just a second. It enqueues a message for the monitor. And it enqueues a connect message unless we've already received a message. So the reason we do this, we could do this back here in the post init, and we did for a while, but we found that a lot of our hardware devices were connecting and never sending anything. So we got a lot of stutter on the line. So we didn't actually send anything to the monitor until we actually started receiving data. So the first time through, we want to tell the monitor, hey, we got a connect going on here. We mark the message as received. We take the data, we decode the frame. This removes control characters and new lines and odd things that are inserted in the protocol just for transmission purposes, decodes the frame. And then the decoded frame then is sent as message data to, and this will internally call enqueue with data and the decoded message, and that will go to the monitor. So every time we receive a line from a drone, we just forward it to the monitor. That's essentially what we're doing here. Unbind is simple. If we've received any data whatsoever, we go ahead and tell the monitor we're disconnecting. And then we delete ourselves from the global hash that references this session. Since we are shutting down, we want to make sure we remove ourselves from the hash. Here's the private enqueue message that takes data and serializes it, creates an array of connection ID and data, converts it to JSON, and then send to monitor. That sends the data, the serialized data, to the monitor portion of the program. So that's fairly straightforward. All right, cool. Questions?
Yes.
Yeah.
Why were there 2 arguments and not 3 for 3 dimensions in the function where the drone is reporting its location?
Because we only have a 2-dimensional display for our drones. So, and what we've discovered in real life, if one drone is above another, the wash from the upper drone totally destroys the lower drone. And in fact, they both go careening off towards walls. So for our purposes, 2 dimensions is enough. And for this demo, it's enough. So let's go and see this at work. So I actually wrote up this software for real. And I got 3 screens here. And oh, I'm going to have to move this guy over a little bit there. Okay, so on the bottom screen, I'm going to run the drone manager, the thing that sits between them and passes messages back and forth. So he started now. This is using the event machine version. Up here, I'm going to start the drone monitor. And he goes and he blanks the screen because he's ready to go. And over here, let's go ahead and let's connect up to this monitor manually and just see what happens. So let's telnet to localhost port 8090. We've got a connection. I'm going to send my position as position 55. And I can, in Frown, it allows you to abbreviate down to 1 character. So there we go. The monitor detected a new drone, but he doesn't know the name yet. So he sent a name question mark message back over here, and I see that in my telnet session. So, oh, now I got to tell him his name. My name is X. And I do that, and the monitor updates the name of the drone just like that. And I can sit here, and I can move the drone around like that. Position 5-4, position 6-6, and the monitor just updates the position that the drone is reporting. Now that's cool with 1 drone, but what if we had more drones laying around? So I actually have a drone program right here. Let's run that. Ruby-i-lib bin drone. And this will be drone A. No, let's call him plus. Drone plus. And that program, once a second, will update the position and send it out on the TCP socket to the server he's connected. And the monitor picks that up and runs. That's kind of cool. Well, 2 drones are cool. How about, oh, let's make them crash. Can I make them crash? So he looks like he's in about position 2-5, position 1-7. Crash, yes. So notice I got the crash message here. That means I have to disconnect, and it says drone X disconnected. We'll flip over here, and we see we got the message drone plus was flying, drone plus crashed. Awesome. Well, we also have a fly message, and let's be bold. Let's start up 20 drones. So this is just a little script that runs the drone program 20 times in the background. I now want to equip my simulated drones with lasers and have them battle it out. I think that would be fun. But so here's a framework for that kind of thing. And this is actually very, very close to what we did for our client in allowing his connections to be made. We had a text protocol that we had to use. We had to respond to all the messages, pass them on to the queuing mechanism so it got into our database, and very, very similar to what we're doing here. If I let that run long enough, eventually all the drones will crash because they're just doing a random walk, and they will crash eventually. Let's just leave that run for a while. Let's go back to our slides. So that's the demo. So what do we like and what do we not like about this particular solution? Well, number one, it handles a bazillion connections. We really can truly handle 1,000 connections with our application, and we do that. We did stress tests on it, and we had 1,000, we didn't actually have the real hardware devices, but we did simulate 1,000 hardware devices coming in to our servers, and we handled it quite readily. There was not a problem doing this in Ruby using Event Machine. It was mainly I/O bound anyway, so the Ruby processing was minimal. Ruby just got out of the way and let the data flow through it, and it was a very easy solution. Like I said, we had a 10x savings in the number of lines over the Java solution. And the Java solution, the Ruby solution were very similar. They were both evented solutions. The Java system had a little more smarts in it that it did some extra handling of the messages, but not that much that I think it throws the comparison out of whack. Other thing we like is the whole thing is single-threaded. I don't have to worry about locks. I don't have to worry about mutual exclusion. I don't have to worry about race conditions because the whole thing runs in a single thread, and that makes programming it really, really easy. And this is one of the nice things about evented programming. One of the things I don't like about this solution is that it's single-threaded. Yeah, it's a blessing and a curse. If it's single-threaded, that means it cannot take advantage of all the cores that I have on my system. My laptop here has 4 cores and they're hyper-threaded, so essentially it could have 8 things going on at once. And out of those 8, I can use 1/8 of the entire processing power of my laptop to do this. Now, on an I/O-bound system, that might not make a difference. But on other situations, that might be a big deal. The other thing I don't really like about it is that you have to warp your mind into this whole evented style of programming, and it's a little bit different. For example, here's a program I didn't show you earlier, but here's when someone requests our drone session to shut down. We go and we log the reason he's being shut down, and then we set a timer for 5 seconds. And you say, okay, in 5 seconds, close the connection. That'll let any outgoing messages get out of the way and lets it quiet down a little bit before we actually do the shutdown. So this closed connection is a callback. Everything that happens asynchronously in an evented program has to be put into a callback to be called later. Now this is not bad, but if you had something like this, so the timer needs to do something, that something is also asynchronous, and when it's done, it's going to return a result. Then you have to make a decision off that result that to do something or something else, and those are and you have this crazy, crazy, crazy nested callback scenario. And there's actually a name for this thing. It's called callback spaghetti. And if you're not careful, your programs will suffer from this. Now, there's techniques to get around it, but it's something that you have to manage, and it's a different way of thinking than the straightforward linear thought that we're used to programming in normally. How'd this slide get in here? Okay, so why don't I just write a threaded program then? What's the problem with writing threaded programs? Well, real quick, you probably all know this anyways, but let's just discuss the scenarios. The problem with threading is that when 2 threads share mutable data and try to change the data, you have the possibility of a race condition. If you don't carefully control how that shared data is updated, you're going to run into problems. Missing updates or inconsistent updates, or something's going to happen. Now, there's a couple things you can do. You can say, well, forget it, let's just use a single thread, but we already talked about the problems with that. You get this kind of chart on your activity monitor. I produced this chart by saying loop do end in IRB, and that's exactly what you get. You can write locks around your shared data. The problem with this, this is a standard thing, and everybody knows how to do this if you've done any threaded programming at all. But the problem with this is it requires cooperation from all the threads. If you forget to access the lock, to acquire the lock before you mutate the data, you're screwed. You also, this solution doesn't compose. It's difficult to hide the fact you're using a lock inside of a module. It's hard to hide it because there are different things that might need to be atomic together, and it's just really hard to compose lock-based solutions. And you run the risk of getting deadlocks. This thread could lock a resource, that thread could lock a resource, and then they each try to get the resource that the other guy has. That's a deadlock condition. They can't proceed from that. And that's a real danger in threaded programs. Okay, so maybe we can solve it by not sharing data. If the problem is shared mutable data, then let's not share our mutable data. And that leads, well, one solution is the process scenario. And this is what Unix does. You just run multiple processes. They get each their own mutable state, and they never share it, so there's no problem. And if you want to communicate, you use something like message queues or something between the two. The problem with this scenario, and this is how Rails works a lot these days. We scale Rails across multiple CPUs by just running a lot of Rails processes. The problem with this, it's rather heavyweight. That's an entire Unix process you're using just to get that parallelism. It uses up a lot of memory because each process has its own memory, and that can be alleviated to a degree by copy and write solutions and things like that, but it's still using up memory, and communication between the processes is difficult. If you need a lot of communication, this is a hard thing to do. Here's a solution that Clojure uses. If shared mutable data is the problem, let's use immutable data. And this works. Clojure is a functional language. It does not mutate its variables by default. So it's very easy to share data between two Clojure threads and not have a problem because you don't ever change the data. You just rebind variables, and that's a local thing. It doesn't affect the threads. If you do want to share data, Clojure says, let's put it in a transactional, a software transactional memory cell. And this is a special thing that is guaranteed to be atomic when you change it. And there's all kinds of mechanisms to make that whole thing work. But if you need to share it, we'll use this special thing. Otherwise, the default is to not mutate our data. And Clojure actually has a very, very, very good story for parallelism. And I'm very envious of them for that reason. Erlang says, OK, we won't mutate and we won't share. So all communication in Erlang happens between threads by putting little tiny messages on a message queue, and then the thread here sits and reads its mailbox and says, OK, now I'm doing this, now I'm doing this, now I'm doing this. So within the thread, within the process of an Erlang process, he is handling one message at a time, but parallelism is going on because the communication is by message back and forth between processes. And that turns out to be a really good model. So what works well with Ruby? I'd like to talk a little bit about something called Celluloid. Celluloid is a library written by Tony Acieri, I believe is his name. That's how you say his name. And Celluloid is an Erlang-like actor-based solution for threading. Here's an example right out of the Celluloid page. We're creating a class called Sheen. We include Celluloid, and that turns this class into a Celluloid actor. That means when you call methods on the Celluloid actor, these messages actually, when you call this, it actually sends a message into the mailbox of the Celluloid actor. The actor pulls that message off and calls the internal objects method, and then returns the result by another message going back. If you want to, you can say async, and that does the same thing, but does not wait for the return message. So you can say, go off and do this, and whenever you get around to it, that's fine. I'm going to go off and do something else while you're processing that message. And then here, the report returns the status. So this will set the status. This will queue up another message. So once this one's handled, this report goes in and gets the result of that. And it's a very, very, very nice system for handling parallelism. Now, the beauty of this is that within an actor, within a Celluloid actor, it's a single thread processing all that data. So you don't have to worry about locking. Parallelism happens between actors, and you have the choice of doing it synchronously or asynchronously style communication between the two. So what if we use Celluloid for our drone solution? Problem is that in Celluloid, every actor is its own thread. And although threads are not nearly as expensive as processes, they are still rather, they're more heavyweight than just a regular object. There's a stack has to be allocated for each thread and all that. So this, creating a celluloid actor for every drone out there, not really a realistic solution if you want to get up to 1,000 drones. However, surprise, the folks who wrote celluloid know this, and they said, okay, let's take this actor model and the way we interact with the world, and let's take evented programming and combine the two so that internally, on a celluloid I/O actor, the whole thing is evented, but you interact with it like a regular celluloid actor, so you can't tell the difference. So, celluloid I/O provides fast event-driven I/O. It wraps all the I/O in celluloid-like actors, so you can't tell you're even using evented programming, and then provides duct tape socket classes so that you can use regular TCP socket calls in your program like you would in a single-threaded program, and you're doing evented I/O and you don't even know it. It hides the evented nature of your I/O from you. So how would the drone session, we'll call it a drone cell now, look like in celluloid? We create the class, we include the celluloid I/O to turn it into an I/O actor. We initialize the thing, we capture the monitor, we create a TCP/IP server. Now we're using regular TCP/IP server calls, just like you would in a single-threaded thing. The difference is that this is actually a celluloid I/O TCP/IP server that knows about evented I/O and will do that under the covers. We store the server for that, we store an array of drones here, and then we say run bang, and here is run. There is run, okay. Run is just an infinite loop that handles incoming connections. Now notice we called it run bang, and here we're calling it just regular run. Celluloid I/O objects, if you call it with a bang method, is kind of like saying to the event loop, schedule the run method to run next, please, after I'm done. Run it asynchronously, and whenever I'm done, queue that up in the event loop so that it happens next. So this will happen after our initialize is done. Run will be queued up to be ready to run. He will go into an infinite loop, and whenever the server object detects an incoming connection, he will call handle connection bang. So handle connection will be queued up to run next. And here's handle connection. This is how we handle an incoming connection. We'll get a socket. We're going to wrap the socket in a line protocol because we want to read it line by line. And sockets don't have a nice line-by-line interface for it, so we write a little wrapper around it to provide that to us. We'll call that iOS. We'll remember the iOS object in our array of drones, and remember this is an internal object. It's no longer a global one. We'll generate our UUID. We will tell the monitor that we're connected to it. This sends the connect message. We then go into an infinite loop to handle data from the drone. Read a line of data, decode it, send it to the monitor, loop back. Read a line of data, decode it, send it to the monitor. Data, read, decode, write. Read, decode, write, over and over and over. This is exactly the processing we're doing for handling a drone. And notice we're doing it in a regular loop. We don't have to worry about callbacks. We don't have to worry about, oh, when is this going to run? We just write straight line logic like we're used to writing in a single threaded application. And all the evented nature of that is hidden behind us. Yeah, and I highlighted these things in red too. I keep forgetting that. Oh, notice here the async call. So that when we send the data to the monitor, we're doing it so here's your data. I don't know if the monitor is ready to accept this data or not, but I don't care. I'm going to send the data, then I'm going to immediately return so I can get my next little bit of drone data to send to the monitor again. So this will send it to the mailbox on the monitor actor. The monitor actor has a similar loop sitting there, reading the incoming messages and handling them. Okay. What we like about the solution, there are no callbacks. It's straight inline regular logic in all our code. It uses the standard TCP/IP sockets or close analogs to those that are really evented under the surface. We just can't tell. You have all the evented efficiency under the hood without having to write event code. And we're all of a sudden using all the cores because these are threads now. It's not a single-threaded solution. This is a multiple-threaded solution. And now we can take advantage of all of our threads. Now, caveat here. You guys know that there's a global interpreter lock in regular Ruby, right? So that means when you're running Ruby code, you only run on one process at a time. However, that's not true in either Rubinius or in JRuby. So if you want to really take advantage of this system with threads, Rubinius or JRuby are good solutions to play with that. Okay, demo again. And I think I got about 10 minutes, is that right?
That's right.
Yeah, okay, awesome. We're working out about right. Let's go back to our demo. And look, all our drones have crashed. I'm not surprised. Let's go down here, let's kill our server. And let's see here. Oops. Bring this guy down a bit here, resize him. Okay. So rather than running drone messages, I got drone celluloid. This is the same drone manager that we saw before, but written using celluloid rather than event.io. We'll fire him up here. We're going to start our server. This is the same server. I didn't rewrite the server at all. He doesn't care what, excuse me, this is the same monitor. He doesn't care what the manager is written in. Event.io or celluloid, he doesn't care. So he's going to be the same thing, and he's running now on a clear screen. Let's go over here. Let's just run a bunch. Let's run 60 drones. Populates them, begins to find the name of each of the drones. They begin crashing all over the place. But it's working quite well, actually. I'm quite happy with that. Cool. Awesome. We'll let that one run for a while, too. Okay, event.io, celluloid.io. So summary, what did we learn? Well, number one, we learned that Ruby is not a one-trick horse. You can use Ruby for a lot of applications, and I think the use of celluloid really opens up the possibilities of using Rubies in environments where we might not have thought about using Ruby before. I'm sure the guys that when they wrote the original Java versions of these hardware managers didn't even think Ruby had the capability of doing that. But because we decided to take a chance, we discovered it did and actually worked very well for doing that. Ruby has a reasonable multi-threaded solution. Now, I don't think it's as good as Clojure. Clojure has an awesome solution, but the celluloid solution in Ruby is actually very reasonable because you limit the interaction to between actors, and within an actor, you're a single thread within an actor, so you don't have to worry about locking within the thread. You reduce the surface area of stuff you have to worry about when you're writing multi-threaded code. So the actor model is a very good solution for Ruby without radically changing the language to be immutable like Clojure is. I think this is probably about the best we're going to get for multi-threaded in Ruby. So that's awesome. And we also learned that flying robots are a lot of fun. Yeah, yay! So is this really practical in Ruby? And I would want to introduce you to a brand new library that just came out last week. In fact, it was announced last week at the LA Ruby Conf, and I was sitting there, and I was talking to Ron Evans. I said, Ron, you've got to see these videos I have of my flying drone and what I'm doing, talking to it with Ruby. He says, Jim, don't say a word. Wait 2.5 hours. So Ron did the closing keynote at the conference, and he got up and he introduced the R2 library. R2 is a micro framework for robotics written in Ruby. It supports talking to Arduinos, Spheros, and Parrot AR drone 2s. Excellent! That's exciting. And you know what? It's based on celluloid and celluloid.io. So it uses that solution there. Here's an example of actually flying a robot by the wire using R2. Create some connections here. Tell the drone to start, tell the drone to take off. After 25 seconds, do this. After 30 seconds, do that, and loop. You could write this more straight line if you wanted to. And here's a picture of, this is Ron, clear over there. He's standing in front of the laptop. They have a bunch of Sphero robots. I don't know if you've ever seen the Sphero robots. They're little round balls, and they roll around. They're controlled by a Bluetooth connection, and they change colors. So he set 7 of these balls on a table, ran an R2 program that talked to each of the balls, and made them, and then he ran, and when they would hit each other, they would change colors. So it was an awesome little demo, these balls randomly rolling all along the table, changing directions in random directions. When they would strike each other, they would change colors. It was a lot of fun. So that was that. They also demonstrated this, and I'm going to show you a video of this. I really wished I could bring my drone here and fly it for you, but that didn't happen. I didn't have enough time to get things set up. But I'm going to show you a video of this. They took the R2-based library and wrote a program that talked to a Wii controller and took button presses from the Wii controller, ran it in the program, and then it would send out commands to the AR drone, and they flew it through the controller, using the R2 program to send the commands out to the AR drone. So let's see that happen. I'm going to turn off sound because you guys probably can't hear it anyways. But there it is. They're flying it totally under the control of Ruby. And that is cool. They said the responsiveness, actually they were using Rubinius to do this one. They said the multi-threaded responsiveness of Rubinius was very, very good. They also tried JRuby. They said JRuby, although faster overall, had a little more latency in it. That was surprising to me. But they were flying it around. They had total control of it. And you got to realize that we were in a car museum. And the Ferraris and Lamborghinis and Aston Martins in the background, you probably had several $1 million worth of cars in the background. They were flying this robot around. At some point, someone runs out and kind of does this, kind of to protect the cars, because he wasn't sure where the flying robot was going. But that's cool. That's real-world stuff done in Ruby, doing robotics. Also, I didn't see over here on the screen. It's off. Let's see if we come back. There's a video feed. So he was pulling video off of the drone and showing it on the screen at the same time. He was pulling down nav data and showing it on the screen. So he was getting all this good data out of off of the drone through Ruby in real time. That was pretty awesome. Let's just skip down here to the landing here. He's coming in, he's hovering, and he's close. And we're down, move it over just a little bit, nudge it over, and down. There we go. That's awesome. That's cool. So, all right. Well, I think I'm done. I'm Jim Weirich. I work for NEO, and thank you very much.